If you missed our discussion on your way in, yes, this is the Schrodinger equation. We're not going to use it. For those wondering, this guy is the Laplacian. It's a vector del. The upside down del itself is a vector derivative. It's just a vector derivative, three-dimensional or multi-dimensional vector derivative. When you square it, it's used for certain things. When it's squared, it's called the Laplacian after a guy named Laplace. But essentially, this side of the equation, this talks about how psi, psi is actually the wave function. You've heard about wave functions. This equation is used to determine wave functions. So the solution to the Schrodinger equation is itself a function, right? You're looking for the wave function. This wave function can then be used to describe a particle's position. If it's used to describe an electron's position within an atom, that's how you get the shapes of the orbitals. It doesn't tell you the exact position of a particle. It gives you a probability distribution of where that particle might be, where it's most likely to be. And that's when you get those weird shaped orbitals, right? There's spheres for the s orbitals, but then when you get to the p, d, f orbitals, they get all weird. One has a donut in the middle, right? Those are all described by that guy right there. This tells you, this operator, this Laplacian, that derivative, tells you how psi, the wave function, changes according to distance. V right here is actually potential energy. We usually use U for potential energy, but in the Schrodinger equation, they usually use V. So it's the potential energy operator. And then on this side, it tells you how the wave function evolves over time, obviously, because you got, this is a partial derivative. Partial derivatives get weird looking D's. Partial derivatives are actually a lot more difficult to deal with than normal derivatives, as you'll learn about when you do differential equations. But the reason I'm putting this up is because this is a differential equation. This is a differential equation Oh, Timothy's.
Wait, so is that I in there?
Yeah, that's I. Yeah.
So basically it doesn't exist.
No, imaginary numbers are very real.
Oh.
Or at least they imaginary numbers are useful for real things. Oh yeah, electrodynamics, like true electrodynamics, it's all about, there's eyes and everything. There's eyes all over quantum mechanics, yeah. What I wanted to show this for, first of all, it's cool, and I had never even seen this before I got to college and started freaking out whenever he started talking about it. So I would have liked to have seen it before I even went there. But the thing is that this is a differential equation whose solution is itself a function. So a differential equation is an equation that involves functions, right? Psi, I put it in blue. Functions and those functions' derivatives. So this right here, the Laplacian or the upside down triangle squared, that is a derivative. So we're talking about the derivative of this guy with respect to position, and then we got partial derivative of that guy with respect to time, okay? And so we have the function and we have its derivatives in a single equation. And then from that equation, we can then determine what that function actually is. Now, what this function actually is, this wave function, is still debated to this day. It's very strange. It's very counterintuitive. It doesn't make logical sense, but this thing works. This thing is, quantum mechanics is by far makes the most accurate predictions when it comes to reality, more accurate than any other theory that we have. So it definitely works. It shows you how smart people are. They figured this out in the early 1900s, right? Before modern technology. How? I have no idea. Simple. People way beyond anywhere I will ever be. But anyway, so the reason I'm pointing that out. What's that?
It's easy, don't you get it?
No, can you explain it to me?
Yeah, obviously.
The reason I'm pointing that out is because we're going to see our first actual differential equation today. And so just get used to, because you're going to take differential equations in college. You're going to be dealing with them for the rest of your scientific academic careers, at least. Maybe not once you're a doctor or other things. But in college, you'll definitely be dealing with differential equations quite a bit. It turns out that most of the equations we deal with are differential equations. Newton's second law is a differential equation, right, involving changes in momentum and stuff like that. So as we'll see today. So before we get there, though.
That's why the more I learn about math, the more I think I know a whole lot of it, and then something like this happens, and it's like, wow, I know nothing.
Sometimes I go in a YouTube downward spiral of just like find on Wikipedia, just look up like tensor mathematics, and then just keep clicking on the hyperlinks, and you realize there is so much math, I haven't watched it yet, but it's in my to watch later list on YouTube. Is what math comes after calculus? The 22 math classes I took after I finished my calculus classes in college. This is a math major, but yeah, I can't even imagine. Anyway, so this unit we are going to talk about simple harmonic motion. Now this block here is fixed, and so if I hit play, nothing happens because this is the spring's equilibrium state. This is an ideal spring. A non-ideal spring has something called damping forces within it. And so if I actually were to grab this guy and move him, this is how real springs behave. It oscillates back and forth, but eventually comes to a stop. I've turned friction off here, so there's no friction. And that's because there's internal friction within the spring that will actually convert the kinetic energy to thermal energy over time. But we're going to turn that off for our initial considerations here. And we're going to talk about Hooke's law. Hooke's law is something we learned in AP Physics 1. We talked about it a little bit, I think, when we did energy. And so what it says, and I'm actually going to put this up. You'll see this at home. That bright spot. Sorry, those people at home, I'm sorry about the bright spot there, but I need to be able to draw on the... That's a little better. Okay, so... Nope. So I have this mass, and again, if I hit play here, the mass does not move because the spring is neither compressed nor extended. So we call this then the equilibrium. I'm going to put it right in the middle of the block. This is the equilibrium position. Oh, those notes aren't for you guys. I'm sorry. If you pick those notes up on the way, and those are for AP Physics 1. That's the equilibrium position for this spring. If I stretch it, if I pull that mass off to the side, and that mass has mass M, I pull it off to the side, I've given it a displacement this way. So I'll call that delta x. I'll just call that x. We'll call the equilibrium point 0, the 0 point for x. So I've just moved it out a distance x. And note that I have a force that is pointing to the left, obviously. So that is a force, and it is exerted by a spring, so we call it a spring force, F, with a subscript SP. Can you even see that? Probably not. And so Hooke's law tells you the relationship between the force and the displacement. Now you should understand intuitively that the farther you stretch the spring, the bigger the force is going to be, right? So that force is not linear. This force does not vary. This force is not constant. That's what I'm trying to say. This force is not constant. The farther you stretch the spring, the bigger the force gets. If it's an ideal spring, it actually does vary linearly with the displacement. Okay. All right. So that's the gist here. And then Hooke's law states that the relationship between those. And notice if I displace it to the right, I give it a positive displacement. What's the direction of the force? Positive or negative? It's negative, right? Positive displacement, negative force. What if I took the block and pushed it this way and compressed the spring? I displacement in the negative direction, the force would be in the positive direction. So we call spring forces restoring forces. You displace an object, the resulting force wants to restore it to its original position. Okay? So that gets indicated with Hooke's law using a negative. By the way, this guy is a contemporary of Newton's. I forgot his first name, last name Hooke, obviously. He was a contemporary of Newton's. He is one of the guys, him and Edmund Halley of Halley's Comet fame. Those are the two guys that said, hey, Newton, why does the moon go around the Earth? Right? And then Newton was like, oh yeah, I've been working on that. It's because of calculus, the stuff that I invented. Right? So he was one of the guys that was essentially challenging Newton, though, to figure that problem out. But he had already largely figured it out, just hadn't told anyone. So Hooke's law, though, states that the force, the spring force here, is negative some constant, k, times the displacement, x. Negative because, well, positive displacement, the resulting force must be negative, right? So that negative takes care of it. If my displacement is negative, then the resulting force must be positive, so that negative displacement times that negative is a positive. Good, good? All right. Now, if we are ignoring all other forces, there's no friction. I turn friction off here. So if I turn friction off, then the only force acting on the object, and the weight force and the normal force cancel out, right? And so they're going to add up to 0. The net force in the y direction here is 0. So because that's the only force, and it's definitely going to cause acceleration, if I hit play here, the block does accelerate, right? And since the block is accelerating, Newton's second law will apply. Newton's second law says that the net force is equal to the mass times the acceleration. The net force here is just a spring force, so that equals the object's mass times its acceleration. And then what I can do is just take MA and stick it in here, right? Now note that this is in AP Physics 1, we're really limited to how far we can go with this type of motion because the force is constantly changing and the position is constantly changing, right? As we watch this, and I'll slow it down and I'll turn the lights off again so people at home can hopefully see it. This force, obviously the displacement from the equilibrium position is constantly going to be changing, but so is the force, right? So to truly describe this motion requires calculus. To describe, in AP Physics 1, we talk about what happens at the equilibrium and what happens at the amplitudes, at the very ends. But in this class, we can actually talk about mathematically the entirety of the motion, okay? So what that means is that this isn't constant, but we do have an expression. This isn't constant either, right? If the force is changing, then the acceleration is also changing. So this force changes, the acceleration changes, the position is constantly changing. So we can tie these together. I can put mass times acceleration in for this force. So I get mass times the acceleration equals the negative spring constant times x. K, if you remember, is the spring constant. It's just a number that measures the stiffness of a spring. Its units are newtons per meter, so it tells you that if you stretch it a certain distance, how many newtons per meter of stretch you'll get, how many newtons of force you get per meter of stretch. All right, this is a differential equation. This right here is a differential equation, and I can write it as such by noting that first of all, x is actually a position function, right? If I hit play on the simulation, the position changes as a function of time. Right? I also know that the acceleration is a function of time. It's constantly changing. The acceleration is also the derivative of the velocity function with respect to time. And it is also, what?
The second derivative.
The second derivative of the position function with respect to time. You don't have to put the function notation of t in there. What? Oh, it's there. It's just really tiny. You don't have to put the function notation there if you don't want to. I'm emphasizing a point in doing this, in that I really want to show you what term or what factors are functions, what part of the equations are actually functions. So you could just put x, a, dv dt, d squared x, dt squared. You could do that if you want. So what I'm going to do is plug this in right here. I have mass times the second derivative of position with respect to time, and that equals negative spring constant times the position function as a function of time. Okay. And just by convention, usually you want. And by the way, this is a differential equation. We have an equation that involves a function and that function's derivatives. Right. This is a differential equation. Usually, in the differential equation, what you're looking for is the function. Right? So solve this equation means to find a function, to find the function that's referenced in the equation itself. There's more to it than that, but this is a good introduction. Now, by convention, usually we want the second derivative part of this particular equation by itself. So we can just divide both sides by m. Okay, and if I divide both sides by m, I get the second derivative of the position function with respect to time equals negative k over m times the position function. And then Huh?
Shut up.
Shut up, phone. That was weird. It's constantly asking me to set up the voice control features, and I do not do that with any technology.
Smart man.
People make fun of me for that, for not being on Facebook. And,
For not being on Facebook?
yeah. Well, I guess nowadays it's cool to not be on Facebook, right?
Because then you're old if you're on Facebook.
Yeah. Well, whatever, Instagram or MySpace or whatever it is now.
Wait, MySpace? Did you say MySpace?
Okay, now I'm also going to write, this is usually how this equation is written too. I'm going to add this guy to both sides, so I'll just have a 0 on one side. So this differential equation usually looks like this. The second derivative of position with respect to time plus spring constant over mass times the position itself equals 0. Okay. Make sense?
So far, so good.
So that is our differential equation. And when you solve a differential equation, first of all, many differential equations are literally unsolvable. Like you can approximate solutions, you can get close. Computers can be used to help find the solutions. It's not like solving for x, right? It's not like doing algebra to solve for a variable. It's more involved than that. It involves a lot more brain power than that, because we can come up with a characteristic solution for this type of equation. We can talk about what the equation means and what type of function would satisfy the equation, and then write that function out and see if it works. Okay. So what type of function, some of you might already know, so if you already know, then shh, Johnny, shh. What type of function, when you take its second derivative and you add it to the original function with some constants in there, what's the only type of function where if you added the function modified by some constants to the second derivative of that same function will give you 0?
Well, it would just be equals a constant, right?
No.
Because it's like derivative. Oh wait, it would only be 0 because the derivative
Is it a natural log or something like that?
Not natural logs. Maybe if there's some weird thing about natural logs that I don't remember. There's a type of function that we deal with a lot, that you've dealt with a lot in your math class, where its second derivative added to itself will give you 0.
Oh, it's logarithmic. Isn't it log? Because if you do sine, and then you do the cosine and then the negative sign. So true.
Logarithmic?
Oh, yeah, I'm thinking.
You're saying the right answer, but you're calling it something else. You're right. What is it? Trig functions. Sine and cosine functions. Right? Is that what you said?
Yeah.
You wouldn't want to interrupt.
Oh, okay. Well, when I'm asking a question, you can interrupt. Yeah. If a function is the sine of theta, the derivative is the cosine of theta. The second derivative is the negative sine theta.
And that
Right?
makes sense because the motion is like this.
Yeah.
Hey.
Right?
Hey.
Makes sense?
Mm-hmm.
So you would say that the characteristic solution is sinusoidal. When you say sinusoidal, it could be sine or cosine. You guys know that. You can take any sine function and make it a cosine function by shifting it, right? By doing a horizontal shift. Of course. So, again, what I want to point out, this is a differential equation. Eventually, you'll be calling them diff EQs. The solutions to diff EQs are functions. And so our solution to this differential equation is a sinusoidal function. It could be either sine or cosine. Sound good? Okay.
Stupendous.
One of the reasons he said not to yell at the answer was because he said if you know the answer, be quiet.
Oh, you already knew the answer? Well, I was thinking if you already knew it from before.
Well,
But if you pieced it together, yeah, I wanted to hear
okay,
it.
yeah.
Remember whenever you took AP Physics 1?
Oh yeah, I do.
I don't even remember physics 1.
I think this was after COVID hit, and so you probably weren't putting any time into your studies.
I have a note sheet.
Okay, I'm just kidding.
It's kind of messy.
Okay, so are we okay with that? We understand that? Now I'm going to keep this up on the board. I'm going to erase everything else, but I'm going to keep this up because we are going to definitely come back to it. D squared. What are you guys doing right there?
Celebrating.
You just win some sports betting or something?
No, we're just gonna solve the equation.
Yeah, we wanted to.
Okay.
Yeah.
So notice this is Hooke's law and Newton's second law combined into a single differential equation. And you saw the motion, right? You let the spring go and it just goes back and forth. And as you pointed out, it's kind of like back and forth motion, kind of like cyclical motion, kind of like sine and cosine functions describe. So, from your math class, you probably remember this. This is from your math class. Y equals A times BX plus C plus D. Right?
I'm going to say y equals mx plus b.
What? Oh, you remember that, right? Remember from math class? The slope-intercept form? The equation of a line.
The first thing that came to mind was line.
Do we need to review that a little bit? Okay. For physics, we have stuff for all this. For physics, first of all, we get rid of the vertical shift, whatever. Vertical shift, put it on the x-axis and you're fine. The horizontal axis and you're fine. For physics, A will still be the amplitude, right? So remember, our function here was our function, position function in the x direction. So instead of y, we write x of t, right? That's going to equal some amplitude. The amplitude, I was going to try and drop, but I might as well just do this again. The amplitude of the motion will be the maximum distance from equilibrium. So if this is my equilibrium point, and I take this mass and I move it here, that will be positive A, and then it will move to, oh, I think I stretched it too far. That'll be negative, the negative amplitude, and it will oscillate between those 2 points. And if there's no energy loss, then it continues forever, right?
If there's no dampening.
If there's no damping in the spring, yeah, it goes on forever. All right? So that's what the amplitude is. So the amplitude is the same from your math class. We use the same letter. We use A. But then B, we use something that we're actually used to at this point, which is very confusing for a lot of students. The thing that replaces B is omega.
I guessed it.
You guessed it, but
Didn't say it out
well,
loud.
B is kind of like that. It's just turn this way and then take that off.
Yeah.
And then we're talking about a function of time, so x gets replaced by t. And then c gets replaced by, typically we don't use it a lot, but it is there. When you do electrodynamics, electromagnetism circuits at a higher level than we will in this class when you go to college, you'll see this a lot because there's a lot of phase shifts and in phase, out of phase stuff when you're dealing with electricity. But it's called the phase angle. It's a phi, P-H-I, phi or phi. Sorry.
We got it. Don't worry.
So A is the amplitude. This guy is P-H-I. What's that, Timothy?
Not the imaginary number stuff you're talking about.
No. You could do this with imaginary numbers too, but we're definitely not going to in this class.
Okay. It's beyond.
That's beyond the scope of this class. So this is phi. Some people say phi. My community college physics professor, who was my favorite teacher ever, said phi, so I say phi. That is called the phase angle. And omega is the angular velocity, but in the context of this type of motion, we usually call it angular frequency. The reason that people find it difficult to talk about what that is, what omega is here, the angular frequency, is because usually when we're talking about angular velocity, we're talking about objects that do this, that go around in circles.
So
Oh my gosh, stop it.
I need your consent.
What? Am I saying something that's like triggering it to?
See, maybe
It wants
it's
to
close to
learn.
Siri, but
So anyway, yeah, so how can an object, because what are we talking about here? We're talking about an object on the end of a spring that's moving back and forth in a straight line. How can this possibly have an angular velocity? What was that, Bradley?
And that's the inverse of the period, right?
Yes, well, it's related to that. It's related to
It's
Everything has angular momentum.
that.
angular velocity.
No, this is angular velocity, though. Not angular momentum.
Angular
Is
I can see where I see it.
no one has angular velocity.
Yeah, true. What was
That
that?
was great.
Timothy?
What about angular time?
for the purpose of
What was that, Timothy?
What's
Angular time, he said.
angular time?
Oh, angular time.
No.
Yeah, well, that's beyond the scope of this class. Too.
Space time.
Okay, so
That's what time bends.
let me try to, because this confused me. Angular frequency, it does, the mass sliding back and forth has what's called an angular velocity or an angular frequency. And I think, kind of, I think having visuals to represent this makes it a little easier to digest.
Yummy.
I know.
Get out of here, you guys.
I know. I mean,
That's weird. Siri is like trying to get you to talk, and then right as you say something about angular velocity and spinning in circles, that starts going up into a circle. I mean, it's confusing.
Yeah, today's world, man, is scary. It's scary. All right, so
Oh my god.
Okay.
kind of see it.
Oh, right.
Okay.
Yeah.
So we could think of this mass as moving in a circle, but we would just say that this dimension is not real. Right?
Oh my god, it makes so much more sense.
Yeah. So you could put like some axes here and just say, well, it's not real. But if it was real, it would be moving in a circle like this, and we call that a type of phase space. But I'm not going to get into that because I really don't understand it that well.
If this
But,
imaginary thing existed, it would be doing that.
Yeah. And it would have this guy right here, these two together. This guy definitely has an angular velocity, right? How many radians per second does it cover? This guy has the same angular velocity because he's moving pretty much in the same. If we restrict this to just its y direction motion, it looks exactly like this, right? Exactly like it. And so even though this guy doesn't move in an actual circle, we say it has an angular velocity. But again, because angular velocity is even weirder than angular frequency, we just say angular frequency. And we measure it in radians per second. Okay? So even though this guy's moving in a straight line up and down, we measure his angular frequency in radians per second. And if you struggle with that, just make the connection with something moving in a circle that's matching one of the dimensions of motion of the object moving in the circle matches the motion of the mass in its vertical or horizontal or straight lining motion. Right?
So how do I like put that into my notes, like that GIF into my notes?
You can't.
Draw
Yeah.
every frame.
I'll make a
Just
flip book.
draw a spring in a squished circle.
There you go. What you might also want to do is look at simple harmonic motion animated GIFs from Flipping Physics, because this is pretty good. Actually, I didn't want to go to here yet. I'm sorry. My bad.
Oh no.
Yeah.
Oh no.
Anyway, yeah, I'm jumping the gun here, guys. You're throwing my flow off. Jeez.
Messing up his harmonic motion.
Yeah, you're screwing my harmonic motion. I don't appreciate that. Okay. So this is what we got. This is what we use for physics. For this class, we pretty much just assume that the phase angle is 0. It's just a horizontal shift, right? Really, it's only important when you have multiple waves existing in the same space, multiple quantities that can be treated with sinusoidal functions existing in the same space simultaneously. So we can just forget about the phase angle for the most part. I'm not going to for the next part of here, but for most of the problems that you'll deal with, you won't have to worry about that at all. All right. So I got everything there. Yeah. So let's talk about, so this is our position function. This is literally the solution to that differential equation. And I'll show you that it is in fact true. But first let's talk about, this is our position function. Let's talk about the corresponding velocity function. The velocity function is simply the derivative of the position function with respect to time. So what's that going to be?
It's gonna be a
Omega A. Oh! I forgot something here, guys.
Oh no.
Square.
Guys, what did I forget?
You tell me. I
The,
don't
the whole point. Sine or cosine. I forgot the sine or cosine here, guys.
Obviously.
No, that's what
That
I
also
was gonna
explains
say.
why I was.
I forgot it here too. Oh my gosh.
Okay, yeah, because I was like, I've never seen this before, but I'm just gonna go.
Oh my
along with it.
It also explains why I was confused looking at my old notes. I was like, what?
Okay,
Oh my
that
gosh.
looks familiar now.
It could be sine or cosine, but I'm going to use sine. Oh my gosh.
Alright.
I can't even blame that on anyone. That's ridiculous. Okay, let's bring it all back together. It's the sine of omega t plus phi. Oh my gosh.
So
Oh.
W or omega.
Hey, editor, can you edit this part out of the video, please? Thank you. I have an editor, right?
No.
Yeah, his name is Mr. Graham.
Oh, dang it. That's why the editing sucks in my videos.
Siri, your editor.
Okay. So, my bad. It's A times the sine. It could be cosine, but I'm going to use sine. You can use either one. It will work. So, what's the derivative of this now? Omega A times...
Cosine of.
Omega t plus phi. Right?
Yeah.
That's the derivative, right?
Mm-hmm.
With that, and it's easy to see here that the maximum amplitude or the maximum displacement from equilibrium is simply the amplitude, right? Because this is you get a maximum x of t whenever sine of omega t plus phi is 1, right? That's it. This can't get no larger than 1, right? So what's our maximum velocity then? What would our maximum velocity be just by looking at this equation? What's the maximum value cosine omega t plus phi can be? 1. That's the maximum value.
1.
And so our maximum velocity is omega times
Omega amplitude.
A. Omega times the amplitude. The acceleration function is the second derivative of position with respect to time. So what's the derivative of this?
Negative omega squared amplitude.
Did you say negative first?
Yeah.
Negative omega squared amplitude times...
Sine
Good.
omega t plus phi.
Good job, brother. And so what is... And here I'll say... Here I really should say magnitude. Or the magnitude of our maximum velocity. The magnitude of our maximum position, right? Because it could be positive or negative depending on what side of the oscillation it is. Yes, sir.
You put the square too small again.
Oh, yeah. I need to write those bigger.
Omega squared a.
Yeah. Yes. So the magnitude of the maximum acceleration would be omega squared times the amplitude. Okay. All right. So that makes sense? Makes sense. So you want to know the maximum acceleration of the... And again, omega is the angular frequency. It's measured? It's measured in radians per second. Okay? All right. So let's talk about the angular... Not the angular. Let's talk about the position, the velocity, and the acceleration functions with this visual from flipping physics, which again ties into
Mr. Graham,
yeah.
is moment of inertia basically just angular mass?
Yeah. You can think of it like that, yeah.
So I wonder if there is an angular time that's some sort of equivalent.
Well, no, okay, angular mass is probably not the best way of saying it, but it's the rotational equivalent of mass. You can define it in a similar way, but time is just a scalar that, I guess mass is a scalar too, but stop confusing me, Timothy.
What about mass squared? What would that measure?
Well,
I don't know.
There kind of would be. It'd be like frequency or something, or period, kind of.
Okay, whatever it is, it's definitely beyond the scope of this class. Okay.
Like Google it. All I get is like angular JS stuff for like unrelated.
So anyway, position versus time graph. We expect it to be sinusoidal, and sure enough it is. Again, ignore the horizontal axis. I just didn't put it right in the middle. But that's what we expect, right? There's our position versus time graph. Let's look at our velocity versus time graph. Velocity versus time graph. Now I think up here, what did I do here? I did... Yeah, so it starts as a cosine. So our position here is a cosine graph. So its derivative should be our velocity graph, so it's going to be more like a sine graph, right? Negative sine graph. So it starts downward like that. And notice how they are out of phase with each other if I plot them together at the same time. And then I'll throw the acceleration function up here too. And I'll slow it down so we can kind of watch it in slow motion.
And they have like the same period to the actual graph itself.
They have the same period, yeah.
Different peaks.
Yeah. Well, that's because the vertical axes measure different things, right?
Yeah.
But the horizontal axes are times, and so they all change at corresponding times, but they don't change at the same time because they are slightly different graphs. So let's slow this down a lot. So we start out, notice I'm starting out at our maximum displacement, right? So it starts out with a maximum position. At the maximum displacement, I have the maximum force, right? Maximum force, because the force gets smaller as the mass moves in. Maximum force means I also should start at a maximum acceleration. But I should also start at a zero velocity, right? And so when I hit play here, it's not perfect, but when I hit play here, I start out with maximum position, but very small slope, because it starts off at rest, right? So the slope on the position function is 0, so it should start out right here at 0. I don't know why it's not. And then I start out with maximum force, so maximum acceleration, so I'm at the maximum acceleration, just the negative, because it's pointing to the left in the opposite direction.
I think you're a bit... I think what happens
Yeah, I
is
think you're a
the
bit
object
under
hits the
max.
side, so then it doesn't go all the way to where you started.
Whatever. It's fine.
So that's why it doesn't start at 0. And also just because the algorithm.
Yeah, there's limitations. So it's like this dance, right? It's kind of like this weird dance. But you want to understand right there, maximum acceleration, maximum negative position, right? Maximum negative position, 0 velocity, maximum acceleration, right? Think in terms of the slopes. The slope here is velocity. Slope there is horizontal. It's 0. So I have a velocity of 0 at that point, right? Double derivative. What's the concavity there, right?
Did the graph that jerk with relation to time?
Not in this program, no. No. Good question, though. So yeah, so those are the graphs. And I feel like, and this is for a mass moving back and forth. This should make it click. At least for me, it really helped. And this is recent. Really helped. That's not us. This is on Flipping Physics. He's got animated GIFs. You just have to say GIFs or GIFs.
Yes.
Thank you.
Ifs.
Thank you.
Actually, it's pronounced Yif. Originally it is.
Are you serious?
Yeah.
Oh.
GIFs.
Well, it's
Okay.
graphic image file,
Jif
so-
is peanut butter. That's
So
our-
notice we have this object on a rotating turntable. And so it matches the vertical position. The vertical position of this object is mimicked by this ball that's just going up and down. And if I follow that ball through time, then it just makes a nice sinusoidal graph, just like the mass on the spring. Okay? And then all these other points are just different points on this rotating object. But this motion right here is exactly what motion this guy would have if it was connected to a spring. and it was oscillating just like a spring. Exactly. Which we can actually kind of see once we go down here a little more. Now we're talking about the linear velocity. The linear velocity of this object as it goes through. And notice, it's kind of weird. Why is it off to the side there? What's going on here? That's internet. Hello.
Maybe it's tracking the position still with,
Yeah, I
with
think
the
he.
dot.
Yeah, I think the
I think
dot.
that's what it is.
Okay.
Dot's tracking position. Because the velocity it's showing on the dot as it goes up. And
Okay, I wasn't doing this last time I looked at this though. Anyway, the velocity,
Correct. I think
the
it
velocity
was
of
correct.
the velocity of this sphere reduces as it goes that way because the spring's pulling it down this way, reaches 0, and then starts picking up speed here, maximum speed at the equilibrium mark. Notice that you can look at these vectors, these velocity vectors, and just think of them as the components, the vertical component of this velocity vector, which never changes magnitude. Right? So again, this is why you can use circular motion and straight line harmonic motion or oscillating motion interchangeably, and you have the same thing. This is why for this object, we say it has an angular frequency or angular velocity. It's obvious that this guy does, but we can treat this guy like he does as well. And the mathematics is pretty much the same, right?
So that makes sense that it's a component. That helps a lot.
Yeah, this visual here is really good. Same with acceleration. Remember, centrifugal acceleration points towards the center of the circle. So it should be 0 at the equilibrium mark, right? Which is when this vector is pointed horizontally, right? It's at a maximum when it's down here because it's purely vertically oriented. And then it's 0 when it gets back to there. But you also want to understand the physics as well. You want to say, well, if this guy's on a spring, right? When he's at equilibrium, the spring isn't stretched or compressed, so this force is 0, so the acceleration is 0. But then when it's displaced its maximum amount, then you have the maximum force, so maximum acceleration. But I just know that as a student, when I was learning this, I knew that the angular stuff with objects that aren't moving in spinny motion or rotating motion, that confused the crap out of me, and I wasn't happy with it. And it wasn't until I saw these visuals, these types of visuals, that it really drove the point home and made it easier to understand. Okay. All right. Another one that I kind of like, and we'll talk about this one. Suppose you dug a tunnel through the earth and you jumped in it.
Oh, it's this.
The neutron star matter.
This is what would happen. If you dug a tunnel all the way through the earth and jumped in, and there's no air resistance or anything, it would act just like a spring, just like a mass on a spring, exactly like a mass on a spring.
Yeah, it feels so weird though.
Yeah, it would take something like 45 minutes to go through it once. Yeah, and you'd be going real fast once you got to the center.
And you'd be crushed.
But what's the net for? It's impossible. We've dug the deepest hole we've ever dug is like 8 miles or something like that. The radius of the Earth is like 6,000 miles. There's no way to do this. But if you could and you jumped in, you would just oscillate back and forth exactly. And we'll do this. We'll do this problem. Well, it's not that bad. It's not that bad.
We'll dig the
What's cool is doing this problem. You end up generating a version of Hooke's law. It looks very much like Hooke's law. You have restoring forces. Okay, you have restoring forces, and there's other situations where it's other situations that you wouldn't expect that have the same type of motion. This guy right here. I mean this you probably would expect. I gotta do this for the people at home. This guy right here is a pendulum. Swing it back and forth. All right, we'll do this tomorrow. Actually, we'll talk about the differential equation as applied. The simple harmonic motion. That's what we're doing right now. That's what this equation talks about. That's simple harmonic motion, and it applies to any object that has oscillating motion that's in response to a restoring force. So a pendulum does that. A torsional pendulum, if I twist this guy, you actually get a restoring torque that makes it spin, and then it overshoots equilibrium, and then it spins back. Right, you've done that before with stuff, right? You twist it up.
Mm-hmm.
and then you let it go, and then it winds up the other way.
I'll do that on a swing.
Yeah, that was fun on swing. And then it spins back. So that's a torsional pendulum. Same thing. This guy right here is called a physical pendulum. This is like your grandfather clock. That's called a physical pendulum. Right? Obeys the same differential equation. Torsional pendulums are interesting. That's how Cavendish determined what big G is. The experiment where he could actually measure gravity on the Earth. He couldn't actually have it affect the motions of objects by a measurable amount, but what he could do is hang from the ceiling. Say we're looking top down. He hung this long rod with two small spheres on it by a quartz thread that was known. The physics of the thread was known. Put very large spheres here and here. Gave it a little nudge, and then it started. So you got an attractive force to here, but then it would overshoot the tension, right? And then it would start oscillating back and forth as a torsion pendulum. And by calculating the frequency of that oscillation, that's how he was able to actually determine the value for big G. So it was simple harmonic motion that let him do that. Did I talk about Cavendish in this class? Cavendish.
Last year.
Cavendish, very, very important, very interesting historical scientist.
I want to talk about Cavendish in this class.
That's what I heard too.
All right, so finish up the current quest homework. If you didn't get my message, I'm adding 5 percentage points on to anyone that finishes or at least attempts all the problems. If necessary, I know it was a tough one. If necessary, I'll provide a curve because it is a major grade. If necessary. So.
If necessary.
Other than that, what's that?